Okay, so in problem number 5 from the chapter review, we've got our typical thing. We're given a function, and then we're told to find the basics of it: increasing, decreasing, local extrema, concave up, concave down, inflection points. So let's attack this one thing at a time. If we're going to talk about increasing, decreasing, and local extrema, we're simply working only in the first derivative. So let's take the first derivative of this function, and we get y prime is equal to the derivative of 1 is 0, derivative of x is 1, derivative of negative x squared is negative 2x, derivative of x, negative x to the fourth is negative 4x cubed. All right? Now that doesn't factor. We don't have good methods for finding the factorization of that. But that doesn't mean that it doesn't have zeros and that we can't find them. Well, it's a cubic, and all cubics have at least 1 0. What with that? Can we graph it? Sure. Let's. So if we go to the graphing mode, we can do a couple of things. One thing that I'd like to have you sort of know is that if I ask you to do things saying analytic methods, you know that you're actually going to have to find the derivatives and show them. But if I ask you just look at it graphically and read off the graph what's going on, then you can look at the graph and say, okay, I can see intervals of increasing and decreasing. So let's start attacking this, looking just at the original function. Okay? The original function was 1 plus x minus x squared. Wait, excuse me, I got all the crap I got to get rid of there. Let's try that again. 1 plus x minus x squared minus x to the fourth. Okay, let's look at this graph in the standard window for just a second. Okay, here's what I say. It looks like it's increasing and then decreasing. It looks like if I asked you to say what is the interval of increasing, you could find the maximum here, and then anything to the left of it is.
Wait, what did you just graph?
This is the original function. This is the.
I thought we were finding the zeros of the derivative.
We're cheating a little bit. We're kind of seeing what we think is going to go on here. All right. All right. So if I asked you just by looking at the graph, where is it increasing? What would you do? How about you find the maximum? Let me find the maximum of this really quickly. Second count maximum. That left bound looks fine. I'll shimmy over to the right. That right bound looks fine. Okay. With a x value of 0.38, I might declare that this function is increasing on the interval from negative infinity to 0.385, and it is decreasing on the interval. Oh, I'm sorry, that's supposed to be the endpoint. And it's decreasing on the interval from 385 to.
How can it be decreasing and increasing?
Okay, it's a legitimate question. Okay. Well, here's the reasoning. We define a function. We say a function is increasing on an interval if given 2 points in the interval. We take the one from the left side first and the one from the right side second. But the value of the right-hand one is large. The value of the function of the right-hand one is larger than the value of the function on the left-hand one. So if I choose any 2 points in this interval, And if I even include that maximum point, and that one's gonna have to be a right-hand point, is it larger than does the function have a higher value than any point that I could choose it to the left of it in that interval? And even though if I'm including that point, sure. Our definition of increasing function says 2 points in the interval, and the one to the right always has a higher functional value than the one to the left. And that's true even at that interval. All right? And the opposite is true for, or the same thing is true for decreasing. It ends up including the interval. So here's us doing that without even doing the calculus part. All right? Okay. Here's what's going on. I'm showing you both ways because on the class I'm going to ask you both ways. I think when I looked at these questions, when I looked at these functions, I feel that they're reasonable. Okay. Problem 3, no. Problem 3, not reasonable. On problems where the functions are particularly nasty in terms of finding the derivatives, how about I say those are the ones that you're going to be able to use graphical methods. Graphical is nice?
It'll be like.
Let's finish this off. Okay, so using graphical methods, we have increasing and decreasing. Now, what if I force you to be analytical? How does our problem change? Well, instead of graphing the original function, what we end up graphing is the derivative function. If you need to find a zero, you're still using analytical methods, but you're finding a zero. Right. So what was the derivative of that function? I believe 1 minus 2x. Oops. 1 minus 2x minus 4x cubed. Okay. Now if I graph that out, this is now the graph of the derivative function. What's important for me for finding increasing or decreasing? Where the derivative is greater than 0 is increasing, and where the derivative is less than 0 it's decreasing. And the 0, I can use my second calc to find that 0.
Spoiler alert, 0.35. Spoiler alert, 0.35.
Well, we know it. We've already done it using the maximum, using the original graph, using maximum. So we know what the answer should be. Left bound, right bound, yes. Boom, same answer. And what do we say? Oh, if I look at the graph of the derivative, I can say f is increasing on the interval from negative infinity to 0.385. Why? Because here's where my 0 is, and the derivative is positive in this entire interval. We could say f is decreasing on 0.385 to infinity. Why? Because the 0 is at 0.385 and the derivative is negative on that entire interval. Are we okay with both of those methods? Yeah. Okay, great. Okay. No, I gotta finish local extrema first. Ready? Local extrema first, then inflection point. Local extrema. Now, we saw from the graph of the original function that there clearly was a local maximum. When we're given information about the derivative, where do we locate the local extrema? Where the derivative is equal to 0, and we see a change from positive to negative.
The local max.
So we're going to get a local max because it's going from the derivative is going from positive to negative at that location. So when asked the local extrema, Where are the zero analytically? Where are the zeros, or where are the critical values for that derivative? And if it's going from positive to negative, like it is here, there must be a local max. I want to finish this and give you the form in which I want you to give me the answer. Okay? Local max at x equal 0.385. Sorry, I have to look at the word max. Max is equal to, now I got to find out what that max is equal to. Okay, here's how I do it. Especially for these ones that got crazy values. My original function was 1 plus x minus x squared minus x to the 4th. Now, I just put that expression in. When I left my graphing screen, I had left it with x telling me where that 0 was for the derivative. That value is still embedded in x. And that's the value of the function at that point. When you leave the graphing screen, having just found a 0 or finding a maximum, whatever it said x equal in the bottom corner, x is still that value when you go back to the home screen. All right? So my answer to that question, there is a local max at x equal 0.385. The local max is 1.215. Great? Now let's get to inflection.
Good morning, Berkeley High School. It's Wednesday, so that is today.
Yeah, for all of you. I announced it in second block, but I didn't have a chance to announce it to you in first block. Would you spread the word? Great. Thanks, Gab. All right. So somehow I lost my derivative. So y prime was 1 minus 2x minus 4x cubed. Y double prime then is negative 2 minus 12x squared. This is going to be a lot easier to do, isn't it? So finding inflection points, finding intervals of concave up and concave down. You look at the second derivative. We're looking for second derivative being positive or negative. Let's see what I get. If I set this equal to 0, I get negative. Is this right?
Yeah.
Yeah, but you're gonna get a negative answer in the square root. So,
No, it was negative, but when I pull it over to the other side,
oh,
it becomes a positive. So I get, when is x squared negative 1/6? Answer, there is no real answers here. Therefore, there's no places where the concavity changes. There's no inflection points.
And then isn't it always
The next question is, so what kind of values do we get out of the second derivative? They're always, no matter what x we choose, they're always negative. Conclusion. Y is concave down for x from negative infinity to positive infinity. Think about the original graph. Didn't it look concave down? It's concave down everywhere. All right, hooray!
and there's no inflection point?
No, and there are no inflection points.